Alright guys, welcome to the class of chemistry. I'm telling you about today the chemical periodicity. It is the topic of AS level chemistry. Uh, what is the meaning of periodicity? Periodicity means the change in properties across the period or down the group and following a regular pattern. A repeating pattern is called periodicity. In this chapter, we will study how the physical and chemical properties of elements of period 3 will show change across the period. This does not remain applicable to the period number 3, but period number 4 can also be used to correlate with period 3 periodicity. So you know that when you move across the period, you can see that there are the elements from group number 1, 2, 3, and now 3 is called 13, and then 4, 14, 15, 16, 17, and 18. So there are different blocks when you move across the period. The first two elements of a period, they are called S block elements because their outermost subshell is S, that is in the process of filling. So that is for group 1 and 2. Then we come across P block elements, which are in group number 13 to group number 18, and group number 18 is also called group 0. We call them as P block elements because the outermost electrons are filling in the P subshell, starting from P1 to P6. There are elements in D block elements as well. In period 3, if you move across the period, you will see that there is no D block element, but in period 4, you will see that after potassium, calcium, then you get scandium, which is scandium, titanium to zinc 30. They are D block elements. They were not given any group number in the older versions of periodic table, but now they are given group number 3 to group number 12. D block elements are transition elements. Just I've told you that scandium, titanium, vanadium, chromium, manganese, nickel, zinc, copper. These are the elements which are D block elements, and they are called transition elements. They form colored compounds, they have variable valencies, and they are used as catalysts. F block elements are quite lower in the period number 6 and 7, and we are not dealing with them in the course of A levels. That we call them as lanthanides and actinides. They are radioactive elements. So let's start with the periodic patterns or periodicity in physical properties of the elements. So first property is their electronic configuration. We have just seen that when you move from left to right, the first two elements are S block. Then in period 3, the remaining elements are in P block. There is no D or F block elements in period number 3, but in period number 4 you also find elements of period of D block elements as well. So first two are S block elements, they are metals. Then you move across the period, you get metalloids, and then you get non-metals when you go from period number 4, 5, 6, 7, and 8, or 15, 16, 17, or 18. The group number 18 elements are also called noble gases or inert gases because their outermost shells are completely filled by 8 electrons and have stable arrangement of electrons. Atomic radii. The trend in atomic radii is that if you see the graph attached in this slide as well, that atomic radii shows a gradual decrease moving from left to right. Atomic radii, in the previous chapter of atomic structure and chemical bonding, we have studied that atomic radii are of two types. They are covalent radii or they are metallic radii. Covalent radii, you have defined it as a distance, half of the distance between the nuclei of two similarly covalently bonded atoms. So, but metallic radii, you don't need to have a covalent bond, but the metallic atoms are as closer as possible, and then half of the distance between the center of the nuclei in a metallic solid. So the unit is nanometer. Whether it is covalent radius or metallic radius, when you move from left to right, atomic radius shows a change, a decreasing pattern. Why the atomic radii decreases from left to right? It is a simple reason, because the number of protons and electrons are increasing, the attraction is increasing, effective nuclear charge is increasing. whereas shielding effect remains the same, and that's why due to the increased attraction, the nucleus, the protons, attracts the electrons from the outer shell strongly and brings the electrons closer to the nucleus. So that's why the atomic radii decreases from left to right. Next property is ionic radius. Ionic radius, first thing that you know is ions are of two types. They are cations or anions. So, but the trend is that whether it is cation or anion, ionic radii decreases across the period. But the decrease is does not follow a smooth trend as you have seen a smooth trend in the decrease in atomic radii. The decrease is slightly different. For that, we need to understand that when we move across a period, the first few elements are metals. For example, in period 3, sodium to magnesium to aluminium, you have metals. And when metals have more protons and more attraction, due to which, if you go for the ionic radius, they have sodium forms plus one electron is lost, magnesium loses two electrons, and aluminium loses three electrons. So they all the three ions, so Na positive plus 1, Mg plus 2, and Al plus 3, all have 10 electrons, but sodium has 11 protons, magnesium has 12 protons, and aluminium has 13 protons. So greater number of protons for the same number of electrons, the attraction becomes stronger, and that causes the radius of the cation decreasing from sodium to magnesium to aluminum. Then comes element comes our silicon. Silicon also forms a positively charged ion if you consider it as a metalloid. So it is Si plus 4. So its atomic size is further smaller than the size of its atom. Then anions. Anions, you know, they are formed by the gain of electrons. And when an atom gains an electron, the incoming electron causes a greater repulsion to the electrons already present in the valence shell. To reduce that repulsion, the electrons in the valence shell adjust and expands the valence shell and move slightly away from each other to decrease the repulsion due to the extra electron or electrons coming into the nucleus. So anions are always bigger than their atoms. But, but when we move from left to right, after silicon we have phosphorus, then sulfur, and then chlorine. Noble gases, argon does not form either cation or anion, so we leave it. So phosphorus, we know from its valency and its placement, it's in group 15 or group 5, so it gains 3 electrons. Sulfur gains 2 electrons, and chlorine gains 1 electron. So the rule is that greater the number of electrons gained, greater is the repulsion between the electron in the valence shell, and greater is the anionic radius. So we will see in the graphs in the next slide that we will see a trend from phosphorus P minus 3 to S minus 2 to Cl minus 1, again a decrease in anionic radius. But the anions are always bigger than the size of their atoms and of course the size of the cations. So we will see an S-shaped graph in the next slide. So we will see a decrease in the cationic radius from sodium to silicon. Then there will be a very large increase in the size of the anion of phosphorus P minus 3, and then there is a decrease again from from P minus 3 to S minus 2 to Cl minus 1. Next is melting points. Melting points depends on the strength of the bond or the intermolecular forces present in an element. We have seen that when we move from left to right, we first we first observe that the metals are present, then metalloids, and then non-metals. So we know that metals have a metallic bond, and metallic bond of sodium is stronger, but magnesium is even more stronger because it has two electrons in the electron cloud per atom and plus 2 charge, and then from plus 2 to aluminum has plus 3 charge in the cations, and it loses 3 electrons per atom in the electron cloud. So from sodium to magnesium to aluminium, we see an increase in the melting point due to the increase in the strength of the metallic bond. This increase is slightly more appreciated when you go from sodium to magnesium and is less appreciated from magnesium to aluminum, but there is an increase. From aluminum, next element is silicon. And silicon, we know, just like carbon, is a metalloid and it is a macromolecule. Macromolecules have a strong network of covalent bonds. It's a giant covalent molecule with a very high melting point. So its melting point is much, much, much higher, approximately 3200 degrees C, compared to that of aluminum, which has a melting point of approximately 900 degrees C. So there's a very large increase in the melting point from aluminum to silicon. From silicon, then we come across the next elements are non-metals. So non-metals, you know that they have van der Waals forces, weak van der Waals forces or London forces. So the melting point decreases sharply from silicon to phosphorus, but phosphorus exists as P4 and sulfur exists as S8. So from phosphorus to sulfur, there is a slight increase in melting point. It doesn't mean that sulfur has a very high melting point like metals, but it's slightly higher because of more number of protons, electrons, and greater surface area and contact points. Phosphorus is P4 and sulfur is S8. So 8 atoms and 4 atoms. So 8 atoms should have a more stronger attraction, intermolecular attractions. From S8, when you go to chlorine, Cl2, it's a small molecule, so that again the melting point decreases and you have got a lower melting point. And then argon is monatomic gas, so its melting point is further lower compared to chlorine. Trend in first ionization energies. We have seen this topic earlier in the topic of chemical bonding and atomic structure, and based on the evidences of ionization energies, we have come across a new atomic model in which we have introduced the presence of subshells and orbitals. So we have done that earlier, but I'm going to explain it to you again, that how the first ionization energy changes across a period. So this graph you see in the slide is quite a comprehensive graph, starting from the first element going to the 36th element. So you see that in period number 1 we have two elements, hydrogen and helium. The first ionization energy has a higher increasing from hydrogen to helium. The reason is, again, we have studied that when you move from left to right in any period number 1, 2 or 3 or 4, there is an increase in number of protons and electrons. The shielding effect remains constant. Atomic size decreases, we have seen in the previous slide as well. So what happens is that the attraction between the protons and electrons becomes stronger, and this causes the ionization energy, first ionization energy, to be much larger, much larger. So that's why you see that from lithium to neon and then from sodium to argon, there is a general increase in the first ionization energy. The loss of electron becomes difficult due to increased attractions. But the trend is not smooth. Generally, yes, it increases from sodium to argon, or from potassium to krypton, or from lithium to neon. Generally, it increases, but particularly when you move from left to right, there are there are two places in a period where the trend is slightly compromised, a slight deviation is there, and that is when you move from group number 2 to group number 3. Like in period number 3, you move from magnesium to aluminum, or in period number 2, you move from beryllium to boron. You see a small decrease in the first ionization energy. This is due to the electronic configuration. We have seen that in group 2 the electronic configuration is S2, valence shell is S2, S subshell has 2 electrons, which is fully filled. But in period number in group number 3 or 13, the electronic configuration is S2p1, and this one electron p subshell is further away from the nucleus and is more shielded, and therefore the one electron from the p subshell can be easily lost. So this causes a decrease in the ionization energy for p1 electron, and it easily is lost. Then you move from aluminum to silicon, and then silicon to phosphorus. The ionization energy again increases as the regular pattern. But from phosphorus to sulfur, and it's the same thing in period number 2. from oxygen to from nitrogen to oxygen, there is a slight decrease. Why there is a slight decrease from N to O or from P to S? This is because when you move from, if you follow the electronic configuration, phosphorus and nitrogen has p3 electronic configuration. P3 means p subshell has 3 electrons, and all the 3 electrons are in px, py and pz, and they have same spin and they have minimum repulsions, so they have a half filled stable p subshell. But when you go to group number 6 for oxygen or sulfur, they have p4 electronic configuration, and p4 means that px has a pair of electrons, py and pz has one electron. Due to a pair of electron in px subshell, there is a greater repulsion called spin pair repulsion, and that makes the fourth electron to easily lose and get rid of it. So to attain a more stable p subshell with p3 electrons, that's why a slight decrease in ionization energy is there. And if you see the trend, so there is this general trend is that the ionization energy increases, but from group 2 to group 3 there's a slight decrease, and then group 5 to group 6 there's a slight decrease. So next slide, you see that the first graph is the trend showing in the ionic radii. You see that from sodium to magnesium to aluminium to silicon, the cations are quite smaller and the size getting further smaller, and there is this decrease, the line is going downwards. But then for phosphorus P minus 3, the line is quite higher, and then that also shows a decreasing trend from P minus 3 to S minus 2 to Cl minus 1. So ionic radii decreases, but cations are much smaller and they show a decreasing pattern. Anions are much bigger, but they also show a decreasing pattern. The next graph is the melting points I have told you earlier. Sodium to magnesium, the melting point changes quite sharply. And then from magnesium to aluminum, it again increases. Aluminum is again higher melting point, but it's not that much higher. Then silicon or carbon in group 4 has a very high melting point due to giant covalent structure. Then phosphorus P4, its melting point is quite smaller than group 4, and it's even smaller than metals. Then sulfur is S8, it's slightly higher than P4, and then chlorine Cl2 and argon has much lower melting points. Next is electrical conductivity. Electrical conductivity again depends upon the bond, metallic bond. Only metals can conduct current, or carbon in the form of graphite can pass current. Otherwise, non-metals do not pass current. That's a general rule. So you have seen that from sodium to magnesium to aluminum, we have three metals in a period number 3, and again the metallic bond has become more appreciated from sodium to magnesium to aluminum. Therefore the conductivity also increases from sodium to magnesium to aluminum. Silicon is a metalloid. You have heard that it is used in microchips and microprocessors. It is used in this process, so it is semiconductor, and its melting point is much lower than that of all these three metals, but it's not zero. But when you go from silicon to phosphorus, sulfur, chlorine, and argon, they have no or negligible electrical conductivity. After finishing the physical properties, trends in the physical properties, now we are going towards the trend in chemical properties across period 3. But before we start that, just correlating to the reactivity of the elements of any period with the ionization energy. So smaller the ionization energy for metals, more reactive the metals are. It means that metals can easily lose electrons, so it means that they are more reactive. So reactivity of metals depends upon their ionization energy. Lesser ionization energy, they are easier to react. That's why group number 1 are more reactive than group number 2, and group number 2 are more reactive than group number 3, because we have seen that ionization energy increases from left to right, so so does the reactivity decreases. So reactions of period 3, we are going to see the reactions of period 3 elements. So first reaction of these elements with oxygen, minded that when we react, sodium with oxygen, you don't need to heat it. Sodium is quite a reactive metal. But if you heat it and you place it in oxygen, in a jar of oxygen, it starts burning with a yellow flame, yellow or golden flame, and forms sodium oxide. Sodium oxide is you know that it's a metal oxide, and metal oxides are, you know, that they are basic. But sodium oxide is not only basic, it's alkaline, it is soluble in water, and it dissolves in water to form an alkali. Then we react magnesium with oxygen. Magnesium ribbon does not react with oxygen at room temperature, so it needs an ignition. Ignition means that we need to heat it until it starts burning in air. When it starts burning in air, it burns with an intense white light and forms a white solid, or whose formula is MgO and its name is magnesium oxide. Magnesium oxide is basic, but it's not alkaline. It doesn't solid in water. It is used as the milk of magnesia. Aluminum, you know, aluminum is quite reactive, and it reacts with oxygen in the air to form a non-impervious or non-porous oxide layer of aluminum oxide, which protects it. And if you want to react aluminum oxide with anything, you need to remove that layer of corrosion or rust from aluminum oxide. But when aluminum oxide, clean aluminum oxide is heated, it burns again with a white light to form aluminum oxide, which is a white solid, which protects it from further reaction. Phosphorus, red phosphorus, silicon is also a metalloid. It's not you see. Silicon also burns with a white light to form silicon dioxide. Phosphorus is quite reactive. It immediately catches fire on slight of heating to form phosphorus oxide. And phosphorus oxide is, you know, that it's a non-metal oxide, so it is an acidic oxide. It dissolves in water to form phosphoric acid or phosphorus acid. So P4O10 is a formula of phosphorus oxide. Sulfur, when burns in air, in oxygen, it burns with a blue flame. It burns with a blue flame to form sulfur dioxide. Sulfur trioxide does not form by burning of sulfur dioxide. Yes, sulfur dioxide can be converted to sulfur trioxide using contact process, using radium 5 oxide catalyst, or it can be also catalyzed in the air by nitrogen oxides to form sulfur trioxide, which then reacts with rainwater to form sulfuric acid. So sulfur dioxide and sulfur trioxide both are acidic oxides, and their inhalation is quite dangerous for our respiratory tract, and they are also soluble in water to form acid rain, which can damage the marble buildings and other structures and your crops. Then the reaction of elements of period 3 with chlorine and their properties of their chlorides. Sodium burns with chlorine again with a yellow flame to form sodium chloride, which is a soluble chloride. Then magnesium burns with chlorine to form magnesium chloride. Aluminum burns with chlorine to form aluminum chloride, which is a white solid. All of them are white solid. Silicon, when it is heated in chlorine, it forms SiCl4, a volatile liquid. Phosphorus, when reacts with chlorine, it forms PCl3 or PCl5, and PCl3 is a volatile liquid, colorless. PCl5 is made when there is an excess of chlorine, which means that further oxidation of phosphorus can take place to form PCl3 to PCl5. Uh, Reaction of these period 3 elements with water. In this case, we will be dealing with the reaction of sodium and magnesium only. The rest of the elements do not react with water. Sodium, you know that it's an alkali metal. It reacts with water to form sodium hydroxide, NaOH, and hydrogen gas is released. The reaction is quite violent. If a larger piece of sodium is used, the reaction is exothermic, and hydrogen may cause explosion due to the heat produced by the reaction. Or otherwise, sodium floats and then easily melts and leaving the alkaline solution. Magnesium does not react with cold water appreciably. It takes many days to collect 100 centimeter cube of hydrogen gas from magnesium. The products in cold water at RTP are magnesium hydroxide and hydrogen gas. Magnesium hydroxide is a white solid which settles down and does not dissolve completely in water. So to increase the rate of the reaction, we will react magnesium with oxygen when magnesium is for steam to form magnesium oxide and hydrogen gas. So you need to react steam. So now the reaction will be appreciable, but the product is slightly different. It's MgO and H2. So magnesium is quite less reactive. So when MgO is formed only when you heat it, and you know that from steam. Next is the structure and bonding of oxides and their reaction with water. So we know that sodium oxide is an ionic compound, giant ionic lattice structure, and it is soluble in water to form alkali. The pH is 12 to 14. Sodium hydroxide is formed. Magnesium oxide is also giant ionic lattice structure, but it is insoluble in water, and its pH is 9 to 11. So it is partially soluble or sparingly soluble. Aluminum oxide is, you know, that it's also giant ionic lattice structure, but some amount of covalent character is there due to the covalency. It is insoluble in water. Phosphorus oxide is a covalent bond, covalent compound, and it reacts vigorously with water to form phosphoric acid, and the pH goes down to 2 to 4. Sulfur dioxide is also acidic. We have just studied by earlier. Sulfur dioxide is also acidic. Chlorides, structure and bonding of chlorides and their reaction with water. So sodium and magnesium chlorides are giant ionic, but when we add sodium chloride or magnesium chloride to water, they just ionize and do not react with water, so they are not hydrolyzed. So their pH is approximately 7. Magnesium chloride has a slightly covalency, so the greater the covalent character of the ionic bond, greater will be the ease of hydrolysis. So sodium chloride is completely ionic, magnesium chloride is also completely ionic, so both of them are just ionized to form their ions. They just dissociate into their ions. But when you go from aluminum towards and further towards the right side, all these chlorides are easily hydrolyzed because of their covalency and covalent character. Just the case of aluminum chloride, AlCl3 or Al2Cl6, if you add it in water, the pH of the water solution goes down to 3. Why? Aluminum chloride forms, what happens to the solution of aluminum chloride? Actually, it is hydrolyzed. Aluminum chloride is reacting it with water to form HCl. And how it is forming HCl? So AlCl3 reacts with water to form AlH2O whole 6 plus chloride ions. This is a complex ion, and AlH2O whole 6 further dissociates to form AlH2O whole 5, and one of the water molecules splits into OH negative and H positive. H positive ion reacts with chloride ions to form HCl, and the pH goes down to 3. This is more appreciable when we take the example of silicon 4 chloride, SiCl4. SiCl4 is easily hydrolyzed with water to form SiO2 and HCl, and the pH goes to 2. And then phosphorus also reacts with water to form two acids, phosphoric acid and hydrochloric acid. So the pH further goes down to 1 to 2. So all these chlorides are hydrolyzed, but if you see that the ease of hydrolysis increases with the increase in the covalent character of the chlorides. Sodium chloride and magnesium chloride are totally ionic, so for the pH is 7. Aluminum chloride has less covalency, but it is covalent, so it has a pH 3, it forms HCl, white fumes are seen. Same case with silicon tetrachloride or Si4Cl, SiCl4. So it is easily hydrolyzed with water to form SiO2 and HCl, and then comes for the phosphorus chloride, which has forming two acids, phosphoric chloric acid, and the pH goes down to 1. So this is all about the topic of periodicity of period 3 elements. Thank you for listening, and hope to see you soon.